Hey guys, it's Miss Miklos, and today we are looking at section 11.2, and we're continuing to look at evaluating limits. And the first thing we're going to talk about is what can we do if using direct substitution fails, because it is going to sometime. And we talked about this a little bit at the end of our last lecture, but when direct substitution produces 0 in both the numerator and the denominator, so when we get 0 over 0, we call that indeterminate form. And so that's when we know that we have to do something else. And so I'm going to introduce two different methods that we're going to use today. The first is something that we call the dividing out technique. And so what the dividing out technique means is that we can factor the numerator and the denominator and then cancel out any common factors. Once we've done that, then we can go ahead and use direct substitution. So we're going to go through kind of an easy example, but off to the side here, it's like I'm going off the page. I want to go through just some factoring reminders. Okay, so I just want to look at some quick factoring, and I think that we're really good on some of those super basic ones that are quadratic, but I just want to remind us of two that we learned in Algebra 2 that can be a little bit tricky. Okay, and one of those is when we have either our sum or difference of cubes. So I just want to remind you guys that this is a pattern, and we use the word SOAP to help us remember what to do. SOAP stood for same, opposite, always positive. So our pattern goes AB, A squared, A times B, B squared. So in this case, since I have a plus sign, it would be same, opposite, always positive. Okay, so that is something that we are going to see sometimes. The second thing we're going to see is what we call factoring by grouping. And this is another concept we learned back in Algebra 2. And this is when we are factoring something that is a polynomial that has 4 terms. So the way we go about doing this, I'm going to group my first 2 terms together plus group my second 2 terms together. So I'm going to look at my first group and see what is my GCF. And in this case, I can take an x squared out, so I'm left with x plus 1. In my second group, I can factor out a negative 2, so I'm left with x plus 1. Now, in reality, this is one term, this is a second term, so I notice that they both have an x plus 1 in common. So I would factor out that x plus 1, and I'm left with x squared minus 2. This is how we would go ahead and factor something like that. So if you guys need more help in factoring, honestly, you should let me know, and I can send you some videos to watch that I made on just factoring back in Algebra 2, and that could be really helpful for you guys. So back to example number 1. It says find the limit using the dividing out technique. Okay, and unfortunately, most of the time it's not going to tell us what method to use. So I just want to show us, okay, what if we use direct substitution? So I'm substituting in negative 3 because we're trying to find the limit as x approaches negative 3. And I get 9 minus 9 over 0. So I get 0 over 0. Okay, and this is the big sign to us. This is what we call indeterminate form. And that's what is telling me that we need to use a different method. Okay, so going back to square one here, I'm going to go ahead and write the limit as x approaches negative 3, and I'm going to factor this numerator. Okay, the denominator is just going to stay x plus 3. But with x squared plus x minus 6, I know it can be x, and I need to think what factors of negative 6 add up to be 1. And I'm thinking positive 3 and negative 2. These two factors cancel out. So now what I'm going to do, I'm going to find the limit as x approaches negative 3 of x minus 2. At this point, I can use direct substitution, and I get that our limit is negative 5. Okay, so I'm just going to write off to the side here, the limit as x approaches negative 3 of x squared plus x minus 6 over x plus 3 equals negative 5. And I know this seems like a lot of busy work to continuously write this out, but it's really important that we are showing correct notation. Another useful technique is what we call our rationalizing technique. And this is when we are rationalizing the numerator of the function. So we're really used to rationalizing a denominator, so this is kind of strange that we're going to rationalize the numerator. But I just want to remind us that it involves multiplying the numerator and the denominator by the conjugate of the numerator. And the conjugate means that we have the same terms and a different sign. Okay, so if we look at number 2 here, it tells me to find the limit as of the square root of x plus 1 minus 1 over x as x approaches 0. So I would always start by using direct substitution because that makes our life easy. But what we see here is I get the square root of 1 minus 1 over 0, so I get 0 over 0, which tells us that we need to go ahead and use our rationalizing technique. Sorry, I was getting distracted by my phone. Multitasking is not always a good plan, guys. Okay, here we go. So the limit as x approaches 0 of the square root of x plus 1 minus 1 over x. I'm going to rationalize this by multiplying by the square root of x plus 1 over the square root of x plus 1 plus 1. So this is what we call the conjugate, because notice my two terms are the same. I'm just changing that sign in between. Okay, so when we actually multiply this, okay, I'm going to write the limit as x approaches 0. Okay, when I use FOIL, these two terms multiplied together just become x plus 1. The square root of x plus 1 times 1 is positive the square root of x plus 1. Negative 1 times the square root of x minus 1, with that one a little crazy, would be minus the square root of x plus 1. And then negative 1 times 1 is negative 1. In the denominator, I'm going to hang on and I'm just going to leave this as is because I'm hoping some things will cancel out. And if we look at this, the square root of x plus 1's cancel out and these 1's cancel out. So I'm only left with x over x times the square root of x plus 1 plus 1. So I'm actually going to go ahead and write that. So I have x over x times the square root of x plus 1 plus 1. At this point, I can cancel these out, and I know that that's going to be a 1 in the numerator, and now I can use direct substitution. So I get 1 over the square root of 0 plus 1 plus 1. I know that the square root of 1 is 1. 1 plus 1 is 2, so I get 1/2. So we're going to say our answer is the limit of the square root of x plus 1 minus 1 over x as x approaches 0 is 1/2. So we're not doing a lot of examples of these because quite honestly, it's pretty repetitive. So anytime you think that it looks like this type of method, I would come back, watch this video, check your notes, make sure that we are on the right track. Another type of problem we'll see quite frequently is a complex fraction. And in order to simplify a complex fraction, we would need to multiply by the overall LCD and simplify that before we use direct substitution. So we'll kind of see a variety of things that sometimes we just need to simplify before we actually substitute in. Okay, so another thing that we can do is use technology. So we have a few methods. One method is that we can use the table feature or we can use the trace function to help us out, and I'm going to show you guys how to do that. And we spent a ton of time talking about this last class, but let's go ahead and look at example 3. Okay, it says find the limit if it exists. I'm going to start by using direct substitution. So cosine of 0 minus 1 over sine of 0. Just a side note, remember that my calculator needs to be in radian mode when we are dealing with these values. I know that the cosine of 0 is 1, so I get 1 minus 1, and the sine of 0 is 0, so I get 0 over 0, which causes a problem. Okay, so our answer is no, we cannot find this algebraically because it gives us that 0 over 0, the indeterminate form. So I'm going to transition now into my calculator and see what that shows us. Okay, so we're going to go ahead and graph this. As always, we should begin by checking our mode and making sure that we're in radian, which I am. And now I'm going to press y equals, and I'm going to go ahead and graph this. So it's cosine of x, and I made a common mistake there. I should actually put a parenthesis before I do cosine because the numerator should be in parentheses. So cosine of x minus 1 divided by sine of x. So I'm going to start by graphing this. So I'm just going to do zoom 6 just because I want to see what this graph looks like. And it definitely looks kind of interesting. Now, where we really care about, we're finding the limit as x approaches 0. So to be honest, looking at this, it appears like as we approach 0 from both sides that the height at 0 is 0. Now, some things that we can do to double check this. The first is our table. Okay, I'm going to make our table start be at 0 because that's the value we're approaching. I'm happy with my change in the table there, so I'm going to do second table. And what we see here is that values to the left appear to be reaching 0. Remember, this means 5 times 10 to the negative 4th power. Values to the right appear to be approaching 0. So I'm thinking that 0 is our limit here. Now, if I wanted to look back at my graph, if I press on the trace, okay, notice that this is giving me an x value and then a y value. So something that we can do is I can type in any x value I want. So if I want like 0.1, I can type that in, and it automatically tells me what my y value is. So this can be a really helpful thing if I'm trying to find what are the y values as we approach an x value of 0. So I can even go closer like 0.01, and it tells me it's at negative 0.005. 0.001. Okay, so we can go ahead and do that as well. Either way, what I'm seeing here is that it appears that the height as we approach our function from either side is going to be at 0. Okay, number 4. Well, actually, before we do number 4, let's go ahead and write this answer. So our answer was equals 0. So this entire thing would be our answer. Okay, so we need to approximate the limit as x approaches 0 of 1 plus x to the 1 over x power. So if I use direct substitution, I get 1 plus 0 to the 1 over 0 power. And let's be honest, that just makes me sad. Okay, that looks like a mess. So when in doubt, if algebra is not helping me out, I'm going to go ahead and use my calculator. Do you guys like my rhyme there? Okay, anyways, back to the calculator. Okay, so I'm going to go ahead and graph this. So I'm going to press y equals and go ahead and do 1 plus x to the, and then I would put this in parentheses, 1 divided by x. And I'm going to go ahead and graph this. So I press zoom 6 here. And we're trying to find the limit as x approaches 0. And this looks really, really weird to me. So some things that I could do, I could go ahead and press trace. Okay, and I might try like 0.01 and see that there are some values. Okay, it's at 2.7, maybe 0.001, and it's at 2.7. Maybe something like negative 0.01. Okay, and I made a mistake there because when I typed negative, I did subtraction on accident. There we go. 2.73. Okay, so it appears to be getting close to a value. In fact, if I looked at my table here, okay, I'm going to make my table start at 0 again. I'm going to go ahead. And if we see this, it appears like it's getting close to this number 2.7196. Okay, from both sides, it looks like it's getting there. Now, you guys may remember that number from somewhere else. In fact, if you guys go ahead and figure out what e to the first power it is 2.7182. Okay, so I'm thinking that maybe this is getting close to that value e. So I'm going to go ahead and in my table startup, I might even get closer. So let's try 0.0001. And I see it's 2.7184. Okay, we see 2.718. I'm thinking that if we get even closer here, so let's make that be at 0, and let's do 0.00001. Notice it's getting to 2.7183. It's getting really, really close to one another here. It looks like those values are the same. And once again, that's really what this number is over here. So our answer here, the limit, is actually going to be the letter, or I should say the number e. So I would go ahead here and say that the limit would be e. Okay, so that's just some more great practice on how to use our calculator. And now we're going to transition into really looking at one-sided limits. So one-sided limits, we've actually already worked with this, but we're going to be a little bit more deliberate in talking about them. Okay, but it's saying that if f is a function and c and l are real numbers, then the limit only exists if both the left and the right limits exist and are equal to l. That's just saying that the limits need to be equal to each other. Okay, we know that if the left and the right side limits do not agree, then the limit does not exist. So I really want to focus here on this particular terminology. Okay, if we look here, it says the limit as x approaches c, and then we have that negative sign. Okay, that means that we are approaching from the left, because we know that negative normally means values that are smaller, so that would be from the left. And our other notation, okay, it says c plus, these would be the limits from the right. Okay, and it's going to be really important that we know this notation. Whenever it asks us to use one-sided limits, we need to show our work with one-sided limits. Okay, so number 5 says find the left and right side limits of f of x as x approaches 0 and use them to determine whether the limit of f of x as x approaches 0 exists. Okay, so we have f of x equals the absolute value of 2x divided by x. So I'm going to go ahead and sketch this. And you guys can sketch this in your graphing calculator if you want. Okay, that's totally fine. We went over how to sketch this last time. But when you sketch it in your graphing calculator, I'm not switching over, we get something that looks like this. Okay, now I drew these arrows. We know in our graphing calculator it would just continue to be a straight line. So the work that I must see from you guys, we're going to see what is the limit as x approaches 0 from the left of the absolute value of 2x over x. So as I'm approaching from the left, it appears that we are going to reach a height of -2. Next, I need to find what is the limit as x approaches 0 from the right of the absolute value of 2x over x. So from the right, it appears that we're hitting a y value of +2. So now, if we look at this, I'm going to say the limit as x approaches 0 of the absolute value of 2x over x equals d and e, because the one-sided limits do not match. Okay, in order to get full credit for a problem like this, I would need to see this work. You can't just show me this and then jump to here. I actually need to see what you think both of those limits are. Okay, so number 6 says find the left and right side limits of f of x as x approaches 1 and use them to determine whether the limit of f of x as x approaches 1 exists. So once again, we have a piecewise function here. And I just want to remind us on a piecewise function, okay, this first part is the function. The second part is our domain. So I'm going to graph this by hand here. Okay, obviously my graph's not going to be super accurate, but it will do. So this first part of our graph, okay, it's telling us the function is 4 minus x. So off to the side, okay, I have y equals -x plus 4. And it's telling me that it is to the left of 1. Okay, so if I graphed this, I know that I'm going to have to figure out, okay, what is the value at when x is 1? So I'm going to plug 1 in. So I get a value of 3. So 1, 3 is an ordered pair. It's going to be open. And the reason why I know it's open is because it just says less than. It does not say less than or equal to. Okay, this is to the left. So a slope of -1, normally we go down 1 to the right 1. I'm going to go up 1 and to the left 1. Our second one, okay, I'm going to have y equals -x squared plus 4x. So I'm going to go ahead and plug in 1. I don't know why I wrote 0 there. So I get -1 plus 4, which is 3. So I get 1, 3 as an ordered pair. And then I know that it's going to go like a parabola, except I made a big mistake there. It should be going down because it is negative. So it would be something like that. And I don't know exactly what it looks like, and that's okay. Because we really care what is our limit as we approach 1. So what I can say here based on the graph, the limit as x approaches 1 from the left of f of x is equal to a height of 3. The limit as x approaches 1 from the right of f of x is also equal to a height of 3, because we can see from both sides it's going to 3. Therefore, we can say the limit as x approaches 1 of f of x is equal to 3. Now, I went ahead and graphed out this entire piecewise function, but we actually did not need to do that. We could have just looked on both sides here and substituted 1 into both equations and seen that it was going to 3. So either way would give us the same exact answer there. Okay, so our final problem today, we are actually looking at a real-life application. So number 7, it says to ship a package overnight. And I know you guys don't have to ship much stuff, but let me tell you, it is expensive. Okay, this delivery service, which will remain unnamed, charges $17.80 for the first pound and $1.40 for each additional pound or portion of a pound. Let X represent the package's weight and let f of X represent the total shipping cost. So it says write a piecewise function to represent the cost of shipping a package that weighs 3 pounds or less. So I'm going to have f of X equals. Okay, we know that it costs $17.80 if it is between 1 pound and 0 pounds. Okay, if it's exactly 1 pound, so I'm using this equal sign, it would be $17.80. Now, as soon as we go anywhere over 1 pound, up until equal to 2 pounds, it brings us into a new price range. In fact, it tells us it's going to cost $1.40 more. So that would be $19.20. Then, if we go past 2 pounds up until 3 pounds, it would be $1.40 more, so it would be $20.60. Okay, so this is an example of a piecewise function. Now, it says graph the piecewise function and label the x and y axes appropriately. So, here is my x-axis, and that is going to be the weight. Okay, that is our independent variable. That's something that we can control. Now, you guys may see this in science sometimes, but when we have like a gap in data, we kind of use this weird line, and that's what this is showing. Okay, so I have 17, 18, 19, 20, 21. Okay, and I'm going to label this Y, and it is the cost. So if I'm graphing this, okay, it costs $17.80 from 0 up until 1. As soon as we get past 1, it jumps up to $19.20 up until 2. And then at 2, it jumps up to $20.60 up until 3. Okay, now obviously this is a homemade graph, so it's not completely to scale, but hopefully we are understanding kind of the way that this is going to work. Now it says show that the limit of f of x as x approaches 2, there we go, does not exist. Use the left and right side limits in your explanation. Okay, so I'm going to start by finding the limit as x approaches 2 from the left of f of x. So from the left of 2, it appears that our height here is at 19.20. Then I need to find the limit as x approaches 2 from the right side of f of x. So from the right side, as I approach 2, it appears that our limit, or our height, is going to be $20.60. So I can definitely see that these two numbers are not equal to each other. So we would say the limit of f of x as x approaches 2 equals does not exist because the one-sided limits do not match. And that would be our final answer. Doesn't he look happy to be delivering packages there? So anyways, this is an example of a real-life piecewise function and a real-life example of a limit. So kind of to recap today, we talked about one-sided limits. We talked about when direct substitution fails, how we can use our calculator, we can use dividing out, and we can use the rationalizing technique.